Welcome to CSC 201, Lesson 8.3, Equivalence Relations. An equivalence relation is a relation that is reflexive, symmetric, and transitive. If you satisfy all three, you're called an equivalence relation. So I want to show that congruence mod 3, mod is short for modulo, which I've defined below, is an equivalence relation. So we're defining a relation T on the integers as follows. For all integers m and n, m will be related to n if and only if 3 divides m minus n. So I want to show that this is an equivalence relation, which means I have to show three things. It's reflexive, it's symmetric, and it's transitive. So let's start with reflexive. So suppose I have an integer a. So I'm curious if a is related to a. That's what reflexive means, right? So I want to know if a is related to a, which means 3 would have to divide a minus a. And a minus a is 0, and 3 divides 0. So we'll just write that out. So we'll say observe that 3 divides a minus a because 3 divides 0. Therefore, a is related to a. And we have reflexiveness. Okay, symmetric. Okay, so now I want to show, to be symmetric, I would need a is related to b, means that b is also related to a. So let's pick two random a and b. A and b are elements of the integers. If a is related to b, that means 3 divides a minus b. Thus, a minus b is a multiple of 3 and now we can observe the thing I'm interested in, right? I want to prove, since I want to show that if this is true, if a is related to b, then b has to also be related to a. For b to be related to a, b minus a has to be a multiple of 3. So let's look at b minus a. b minus a is just the negative of a minus b. And a minus b is 3 times an integer, 3 times k. So we can write this as 3 times negative k, and negative k is an integer. Okay, since the opposite of k is an integer, 3 divides b minus a. Therefore, b is related to a, and we have symmetry. Okay, transitive. Last thing to prove is transitive. All right, so now for transitive, I have if a is related to b and b is related to c, then I have to prove a is related to c. So I'm going to suppose a, b, and c are integers, and a is related to b, and b is related to c. Okay, so what it means for a to be related to b is that 3 divides a minus b, and because b is related to c, 3 divides b minus c. And those statements tell me that a minus b is a multiple of 3, and b minus c is a multiple of 3 as well. Now, observe that A minus C is the thing I'm interested in. I want to show that A minus C is a multiple of 3, because that's what it means for A to be related to C. I'm assuming A is related to B and B is related to C. I have to prove that A is related to C. And two elements are related if their difference is divisible by 3. So I need to show that A minus C is divisible by 3. So A minus C, I'm going to do a little trick here, and I'm going to say, well, A minus C, I could write that as A minus B plus A minus C, right? Because, A minus B plus B minus C. Because the minus B and the plus B will cancel, and I'm just left with A minus C. And A minus B is 3K, and B minus C is 3J. So this is 3 times K plus J, which is an integer. Three divides A minus C, and thus A is related to C. Okay, we have a new definition. Suppose A is a set and R is an equivalence relation on A. For each element little a and big A, the equivalence class of A, which we denote with these square brackets, also called the class of A for short, is the set of all elements X in A such that X is related to A by R. In symbols, we say the class of A is the set of all X's in A such that X is related to A. For example, I have A is the set 0, 1, 2, 3, 4, and I've defined a relation R on A as follows. It's just a set of ordered pairs. And I want to draw a directed graph. So to draw a directed graph, I need to start by making a point for each of the elements of A. So let's see, I've got 0, 1, 2, 3, 4. And then 0, 0 is in my set R, so I have a loop on 0. 0, 4 is in the set, so I connect those two. 1, 1, so I put a loop on 1. 1, 3. 2, 2, so 2 gets a loop. 3, 1, send that back to 1. 3, 3, 3 gets a loop. 4, 0, send that back to 0. And 4, 4, so 4 gets a loop. Is this an equivalence relation? Well, I have to check the 3 properties of an equivalence relation. Reflexive. Yes, it's reflexive because every point has a loop on it. Is it symmetric? Anytime you go from one point to another, do you also have an arrow that comes back? Yes. 0 to 4, 4 to 0. 1 to 3, 3 to 1. And 2 isn't connected anywhere, but that's okay. It just says if 2 were connected to 1, 1 would have to be connected back to 2. But the if part is false, so I don't have to worry about that. So yes, it's symmetric. And then transitive, 0 to 4, 4 to 0, 0 to 0. So yeah, it's that little loop there is transitive. 1 to 3 and 3 to 1 means 1 to 1. I'd have to be able to do that directly, and I can. So yes, anytime you can get from one place to another in 2 steps, you can also get there in 1 step. Okay, we want to find the distinct equivalence classes of R. So what does it mean to be an equivalence class? So let's just write down the definition. It says, for any integer A, the equivalence class of A is the set of all x's in Z, oh, in this case it's in A, the set of all x's in A such that x is related to A. Okay, so my equivalence class of A is all the x's that are related to A. So A is like a number that you'll be given, and we have to find all the x's that are related to it. So for example, let's find the equivalence class of 0. Okay, I've just picked an element. This should be an A right here. So I just picked an element of A, started with the first one, 0, and I'm going to find its equivalence class. So it is the set of all x's in A such that x is related to 0. So I can go look at my picture and say, okay, what's related to 0? What has an arrow drawn to it from 0 or to 0? So 4 and 0. 0 is related to 0 and 4 is related to 0. So we just list the elements of A that are related to 0. And then the equivalence class of 1, that would be the set of all x's in A such that x is related to 1. So we look at the picture or we look at the ordered pairs, and I want to find all the x's, like what comma 1 lives in this relation. So 1 comma 1, 3 comma 1, and that's it. So 1 and 3 are both related to 1. And then the equivalence class of 2, what's related to 2? The set of all x's in A such that x is related to 2. So this one's easier to see in the picture. What's related to 2? Only 2 has an arrow drawn to it. So it's just 2. All right, and then the equivalence class of 3, the set of all x in A such that x is related to 3. Okay, what's related to 3? When I look at my diagram, what has an arrow drawn to 3? 3 does, and 1 does. And then the equivalence class of 4, what's related to 4? Look at your diagram, and 0 and 4 both have arrows drawn to 4. Now, I've listed the equivalence class of every element of A. The question was to list all the distinct equivalence classes. So we should notice that a couple of these are the same, right? I have 0, 4 and 0, 4, and I have 1, 3 and 1, 3. So anything that shows up twice, we just cross out because we only want distinct or different equivalence classes. And so I only have 3 of them. So now I want to describe the distinct equivalence classes of congruence modulo 3. So I rewrote the definition here. We proved earlier in the lesson that this was an equivalence relation. So now I want to find all of its distinct equivalence classes. So remember the definition of equivalence class. I'm just going to write it down. It says, for any A, in this case, it's the integers because my relation is on Z. So for any A in the integers, the equivalence class of A is defined as the set of all x in the integers such that x is related to A. Okay, and in modulo 3, what it means for two elements to be related, right? M is related to N if and only if 3 divides M minus N. So this I could rewrite as the set of all x in z such that 3 divides x minus a. And then what does it mean for 3 to divide something? It means that that something is a multiple of 3. So this is the same thing as saying the set of all x's in z such that x minus a is a multiple of 3. And then one last little step, for this looking at this equation, I'm going to add a to both sides. Move this a over to the other side. And so this is the set of all x in the integers such that x is a multiple of 3 plus the number a. All right, so this is a good working definition now to find an equivalence class of a number a. So let's just start with 0. And this works for any a in the integers. I'm going to start with 0. Okay, so in particular, the equivalence class of 0, that would be the set of all x in z such that x equals 3k plus 0. For some k in the integers. Okay, I'm just applying this definition when a is 0. So what this means, x is a multiple of 3. Okay, so if I wanted to list this using the roster method, I would say all the multiples of 3. So like -6, -3, 0, 3, 6, etc. Okay, and then the equivalence class of 1, that would be the set of all x in z such that x equals 3k plus 1 for some k in z. So multiple of 3 plus 1. So I can list all the multiples of 3 plus 1. It would be like -5, -2, 1, 4, 7. Those are all multiples of 3 plus 1. And then the equivalence class of 2, that'd be the set of all x in z such that x equals 3k plus 2. So all the multiples of 3 plus 2, and I could list those, I would have -4, -1, 2, 5, 8. Each of those numbers is a multiple of 3 plus 2. And then let's do the equivalence class of 3. Set of all x in z such that x equals 3k plus 3 for some k in z. So multiples of 3 plus 3 would be -3, 0, 3, 6, 9, etc. And those are just the multiples of 3 again. And if I wanted to do the equivalence class of 4, the set of all x in z such that x equals 3k plus 4. So multiples of 3 plus 4, that would be -2, 1, 4, 7, 11, which is the same as the multiples of 3 plus 1, right? These are the same set. And I'm going to start to repeat because you can only have 3 remainders from when you're dividing by 3. So when you divide by 3, your results can be no remainder, remainder 1, remainder 2. If you have remainder 3, that's actually just a multiple of 3. So if I'm talking about distinct equivalence classes, 3k plus 3 is the same as 3k plus 0. So we can get rid of that one. The equivalence class of 4 is the exact same as the equivalence class of 1, so I can get rid of that one. And my equivalence classes are just these 3, 0, 1, and 2, which are the 3 possible remainders when you divide by 3. So that leads us to our final definition. M and n are integers and d is another positive integer. We say that m is congruent to n modulo d, or mod d for short. And we write it with a triple equals sign. M is equivalent or congruent to n mod d if and only if d divides m minus n. Symbolically, we write m is congruent to n, and we put parentheses mod d. So another way to think of this is to ask ourselves, do m and n have the same remainder when divided by d? So let's do it both ways. We'll answer this question both ways, using the formal definition and then the remainder definition. So 12 congruent to 7 mod 5, true or false? So what this is really asking, because it's saying that it's giving me this statement, and I want to use this to answer whether it's true or false. So my d here is 5. Does 5 divide 12 minus 7? Okay, so the answer is yes. 12 minus 7 is 5. 5 divides 5, so yes. Okay, another way to answer this would be to say when you divide 12 and 7 by both each separately, when you divide them by 5, do you get the same remainder? So 5 goes into 12 twice with a remainder of 2. 5 goes into 7 once with a remainder of 2. So 12 and 7, when divided by 5, have the same remainder. So that's another way to get to the yes answer, that they are congruent. So for B, I'm really asking, does 4 divide 6 minus negative 8? Okay, or does 4 divide 14? And the answer is no. Okay, 4 does not go into 14 with no remainder. And a shortcut for figuring this out is to say, what is the remainder when you divide each of these two numbers by 4? Is the remainder the same? So 6 divided by 4, 4 goes in once with a remainder of 2. And 4 goes into negative 8, negative 2 times with a remainder of 0. So these are not congruent. And then is 3 congruent to 3 mod 7? I'm asking, does 7 divide 3 minus 3? Or does 7 divide 0? Yes. And we can alternatively say, when you do 3 divided by 7, what's the remainder? Okay, so 7 goes into 3 0 times with a remainder of 3, and 7 goes into 3 0 times with a remainder of 3. So yes, these are equivalent.